All right, here we are for test number one's review. Start off talking about some limits. So in this case, here's your graph. We want to take the limit as x is approaching 0 for the function. So the function's graph looks like this. It's actually got these two pieces. And the problem here is that as you approach 0 from the left on the x-axis, you're basically traveling along the graph this way. And the y value that you're approaching is a y value of 1. Now, if we're approaching x0 along the x-axis from the left-hand side, you're essentially traveling along the function this way, and you're approaching a y value of -1. Now, the second you get to 0, you see you get this solid dot here, and the y value is 0. But just because the y value is 0 at x of 0, that doesn't have anything to do with the limit. So the limit's all about what happens as you approach 0. And since I'm approaching +1 from the right-hand side and -1 from the left-hand side, the best we can say is that this limit does not exist. Remember, for your limit to exist, you have to approach the same thing from both directions. All right, here are two limits, and we want to figure out whether or not these limits exist through the analytic approach. And so they both use the same tactic in that what we're going to do is we're going to factor. So if you look at the first one, we have the limit as x approaches 1 of x to the fourth minus 1 over x minus 1. I can factor the numerator using the difference of squares. So I have the limit as x approaches 1 of x squared minus 1 times x squared plus 1 all over x minus 1. That still doesn't do anything for me though. I got to factor again. So I have the limit as x approaches 1 of this x minus 1 right here can factor as another difference of squares. So x minus 1, x plus 1. And I have this x squared plus 1 here, but that can't factor. Sum of squares can't factor. So you have x minus 1 on the denominator. Now these two x minus 1s cancel. So you see, then this is what you're left with. So what we have is the limit as x approaches 1 of x plus 1 times x squared plus 1. Well, now we got to a point where it's just a polynomial. So I can plug 1 in, and what you see is you get 1 plus 1 times 1 plus 1, 2 times 2, 4. There's your limit. The big issue here was I couldn't plug 1 in from the beginning because the denominator would have been 0. But if you look, the numerator also would have been 0, and that kind of tells me that this was the way to go. If I look at this next one here, same deal. X is approaching 1, the denominator is 0. But look what happens if I approach 1 in the numerator is also going to 0. So both are 0. So that tells me I'm going to try and factor this one also. So I got the limit as x approaches 1 of, if I factor the numerator, I'm going to have x minus 1 times x plus 8 all over x minus 1. The x minus 1's cancel. So I have the limit as x approaches 1 of x plus 8. We'll look at that right away. That's going to plug 1 in, and I'm going to get 9. So the limit as x approaches 1 is 9. Okay, these two limits, we have a slight different way of going about it. In both cases, we have a problem of the denominator being 0, just like the last two. If x is approaching 0 here, this denominator is 0. If x is approaching -3, this denominator is 0. So let's focus on number 4 for a second. If you look, when I plug 0 into the numerator, I also get 0. And so this is another 0 over 0 limit, which tells me I'm going to be able to work with this thing, but factoring is not going to be the thing we're going to go with this. What we're going to do here is we're going to multiply by the conjugate to try and move around this root. So you have the limit as x approaches 0 of the square root of 1 plus x minus 1 over x times square root of 1 plus x plus 1 over the same thing. What that allows me to do is when I multiply all this out in the numerator, it's going to use the difference of squares because I'm multiplying conjugates. So if I square the first one, it's going to give me 1 plus x. If I square the second one, it's going to give me 1, and I take their difference. In the denominator, I have x times the square root of 1 plus x plus 1. So look at what happens here. We got 1 plus x minus 1. These two 1s will cancel. So now you look and say, all right, well, all I have is x over x times this. Well, these two x's then cancel. Two steps kind of getting done at one there, but I think you can follow that. 1 over the square root of 1 plus x plus 1. Look now, when I go to plug 0 in, what do I end up with? 1 over the square root of 1 plus 1, which gives me 1/2. Now this other one over here, number 5, a little bit different. Plug -3 into the denominator is going to go to 0, but the numerator is just going to be 1. Well, now only the denominator is 0. Telling me that only the denominator is 0 is basically telling me here this rational function has a vertical asymptote. we have a vertical asymptote at -3. So if you think about this vertical asymptote here, well, let's do it this way. Vertical asymptote, -3 is the x value right here. Well, as you approach this vertical asymptote from the left or from the right, there's only two things that can happen. When you go from the right, you're either going to go up to positive infinity or down to negative infinity. And the same thing from the left, up to positive infinity, down to negative infinity. Now look at this limit. This limit we're trying to approach only from the left-hand side. That's what that little negative up here is talking about. So if we're approaching from the left-hand side, this vertical asymptote from the left-hand side, my function is either going to go up to positive infinity, which means the y value is going to go up to positive infinity, or the function is going to turn down to negative infinity. So I know right away that the answer for this limit is either going to be positive infinity or negative infinity. Question is which one? So what I'm going to do here is I'm going to say, well, if I'm approaching -3 from the left, this value is less than -3. So this total value here, if I take something less than -3 and add 3 to it, that's going to end up being negative. Okay? The numerator is 1, so overall the value of this thing is going to be negative. So if the whole value is going to be negative, I knew the answer was either going to be positive infinity or negative infinity, I could automatically just deduce that the answer for this limit is negative infinity. There's not as much work for this one as there is here. It's more of an intuitive approach to get your answer for this limit. Okay, now for this one, the big difference is that x is approaching infinity. In every previous example, x was approaching some constant number. X is approaching 1, 0, -3. Here, x is approaching negative infinity. The other thing, or sorry, positive infinity. The other thing is that this is a rational function. When it comes to x approaching infinity of a rational function, it's all about basically the horizontal asymptotes for this function. Notice that this function has the same degree in the top and the bottom. So the numerator and denominator have the same degree. When the numerator and denominator have the same degree, the horizontal asymptote is just based off of looking at the leading coefficients. In this case, 3 and -1. So this simply can be seen as the limit is going to equal -3. And again, that's because of all the things that go on with this. Now, another way of getting this done, if you want to do a more concrete way of doing it, is we look at this limit as x approaches infinity. If I divide everything in the numerator and denominator by x cubed, so I have 3x cubed minus 5x squared plus 3x divided by x cubed over -x cubed minus 2x plus 6 over x cubed. I could split this up into 3 separate fractions, this up into 3 separate fractions, and you see that if I take the limit as x approaches infinity of 3 minus 5 over x, that'll simplify out to be, and 3 over x squared, and this becomes -1 minus 2 over x plus 6 over x cubed. Sorry, this was a square here. And I look at the limit. Well, I can take the limit of each one of these pieces here. Well, the idea is the limit of this constant is going to be the constant. Limit as x goes to infinity of this, since the denominator is going to get big, the whole thing's going to go to 0. This one's going to go to 0. This one's going to go to 0. This one's going to go to 0, and that's a constant. So I end up with 3 over -1, which is the same answer we had before. There's no real need for all this work, but if you wanted to see something that had a little bit more computation to it, that would be the way to do it. I would prefer you just look at the degrees and tell me the answer is -3. Okay, here are two functions where we're going to take the derivative. They both should be very easy. First one's a polynomial. We're going to use the derivative of these three separately because they're added and subtracted together, and each one's going to apply the power rule and the constant multiple rule. So very simply, the first one is y prime equals 16x cubed minus 21x squared, and the derivative of 1 is 0. That's it. This one, number 8, we're going to rewrite the function first. I'm going to write this as 4x to the -1 minus 3x to the -2 plus 4/3 x to the -3. That's just bringing all these exponents up to the numerator. Now I can do the power rule on each one. So now my derivative will equal -4x to the -2, positive 6x to the -3. And if I bring this 3 out, it's going to cancel with this 3, but still the negative is going to be there. So -4x to the -4. I'll rewrite the answer so that there are no more negative exponents. -4 over x squared plus 6 over x cubed minus 4 over x to the 4th, and there's your answer for your derivative. So both of these should be very easy derivatives to do at this point. If you're struggling with the power rule still, there's going to be a major problem for you on this test. This problem we can go about two ways. One, we can use the product rule. And since I have two things multiplied together, product rule would be most appropriate. Another way I could do this is I can actually sit here and multiply this all out. I'll get a polynomial and take the derivative of that polynomial. Doesn't matter. I'll use the product rule just so you see a product rule example. So in this case, I want to take the derivative of the first function, which will be 2, times the second function, plus the derivative of the second function, which will be 4, times the first. And then that's my derivative. And at this point, I'm going to simplify it, but I'm done taking the derivative. So now I'm going to distribute this out. So I end up with 8x plus 2 plus 8x minus 20. And I end up with 16x minus 18. Notice that if I multiplied this out in the beginning, I would have had 8x squared. I would have had a minus 20x and a 2x, which would give me a minus 18x. And then I would have had a negative 5. That's just the original polynomial still. Look at it. If I took the derivative of this, you can see easily that this is the answer I would get. So either way, you get the same answer. It doesn't really matter how you get there. Okay, here we're going to use the product rule. And so in using the product rule, we have the first function and the second function. So if I say y prime equals the derivative of this first one, well, the derivative of the first one is going to be 2x minus 5 times this second function here, which will be 5x cubed minus x squared plus 5, plus the derivative of this second function. Well, that's going to give me 15x squared minus 2x. And that's going to be multiplied by the original first function, which was x squared minus 5x plus 2. And so basically that's your derivative. Now, that's not the answer we're going to give because we're going to then distribute all this out and collect like terms. But our derivative is basically done being taken. So we multiply the 2x times the 5x cubed. We're going to get 10x to the fourth. Then we're going to get minus 2x cubed. Then we're going to get plus 10x. Then we'll multiply the negative 5 in. We're going to get negative 25 x cubed. Then we're going to get positive 5x squared. Then we're going to get negative 25. Then we're going to multiply all this out. So let's go with the 15x squared times the x squared. That's going to give us 15x to the fourth. So that's a positive. Then keep going. We're going to get negative. What's that going to be? Negative 5 times 15 is what? 75. 75x cubed. And then plus 30x squared. Then multiply the negative 2x in, which will give me negative 2x cubed plus 10x squared minus 4x. So then you got to collect all these like terms here. So we got an x to the fourth and we got an x to the fourth. So they'll come together. So we end up with what? 25x to the fourth. Then we have an x cubed and an x cubed and an x cubed and an x cubed. So what do we get there? The negative 25, the negative 75 gives me negative 100, plus a negative 2 and a negative 2 gives me negative 104 x cubed. Okay, so then we got x squared, x squared, x squared. So 35, 45. Okay, then we have x and x. So that's going to give me what? Plus 6x. And finally, negative 25. Okay. So that would be after everything's multiplied in and collected like terms, but this is your derivative unsimplified. Here we're going to use the quotient rule. So I take the derivative of the numerator, which is 2x, times the denominator, minus the derivative of the denominator, which is 2x plus 6, times the numerator, all over the original denominator squared. And there's your derivative. To write the answer, we're going to simplify this thing, so I have to distribute this out, and so you're going to get 2x cubed plus what? 12x squared. This negative is going to come in with the 2x plus 6, so I'm going to get what? Minus 2x cubed minus 10x minus 6x squared minus 30 all over x squared plus 6x squared. So take your like terms, put them together. So the 2x cubed, the minus 2x cubed cancel. Squares of squares gives me 6x squared minus 10x minus 30 all over x squared plus 6x squared. Can't simplify it anymore. There's your derivative. Okay, here's another quotient rule one. Same deal. I'm going to find the derivative. I'm going to take the derivative of the numerator, which would be 2x plus 5, times the denominator, which would be 2x squared plus 3x plus 4, minus, I'm going to take the derivative of the denominator, which will be 4x plus 3, times the numerator, which will be x squared plus 5x plus 3, all over the denominator squared, so 2x squared plus 3x plus 4 squared. And there's your derivative. Again, that's not the end of the work, but that's your end of your derivative. Last step is just algebra. We'll distribute all this out. We'll collect like terms, and we'll wrap it up. So we got 4x cubed. What do we got here? Plus 6x squared plus 8x plus 10x squared plus 15x plus 20. And then this is going to distribute out, and this negative, basically everything's going to be negative after we distribute this out. So you're going to get, I'm going to run out of room here, so I'll start putting it here. Negative 4x cubed plus 20x squared plus 12x. Oh, sorry, all these are minus. All these are minus because of this negative. And then we have minus 3x squared minus 15x minus 9 all over that denominator squared. So put these together, you see what happens. Well, 4x squared minus 4x squared, they'll cancel. I got cube, sorry. I got a square, I got a square, I got a square, I got a square. Let's put those together. What do we get? The 6 and a 10 is 16, minus the 20 is going to give me negative 4, and a negative 3 is going to give me negative 7x squared. I got an x, an x, an x, and an x. So 8 and 15 is going to give me 23, minus 12 is going to give me, what's that going to be? The minus 12 and the minus 15 is going to give me negative 27, so negative 27 and positive 23 gives me negative 4x, and then I have 20 and negative 9, which is going to give me, what's that going to be, positive 11, all over 2x squared plus 3x plus 4 squared. All right, so we need to find the equation of the line that is tangent to the graph of the given function at the given value. So here's our function, and this is the x value for the point that we're trying to find. So if we want to actually find the point, we need an x and a y. So to find the point, we're going to take this x and plug it into the function. So we want to find f of 1, and f of 1 would be 1 minus 1 over 1 squared. So that's 1 minus 1, so 0. So the point c, f of c, would be 0 or 1, 0. All right. So we want to find the equation of the tangent line at this point. Well, we need to find the slope of the tangent line. That's where derivative comes in. So in order to find the derivative, we want to take the derivative of this function. Now, if I'm going to take the derivative of that function, it's much easier if I write that function as f of x equals x minus x to the negative 2. Because then we could just use power rule. So if we do that, then our derivative would be 1 plus 2x to the negative 3. And this, the derivative of this is 1, and this power comes out to the front. The new power is negative 3. That's how I got that. And so if I want to find the slope of the tangent line at x equals 1, I need to find f prime of 1. Well, that would be 1 plus 2 times 1 to the negative 3. Well, 1 to any power is 1, so this is 1 plus 2, so that's 3. So that's the slope of the tangent line. So we have the slope of the tangent line, we have our point. So now we're going to use y minus y1 equals m times x minus x1. All right, and we got y minus 0 equals 3 times x minus 1. So y equals 3x minus 3. That is the equation of the tangent line to f of x at x equals 1. Alright, so here's your last one. In this case, we want to find the second derivative. So if we're going to find the second derivative, we need to find the first derivative. If we find the first derivative, we find y prime. Well, this should be really easy. It's a polynomial. So we're going to get 21x squared minus 16x. Then we're going to find the second derivative and get 42x minus 16. There you go. If I said third, fourth, fifth, we could keep going, but second derivative, there's your second derivative. Should be a real easy question. Here's our review for test number 2. We start off with some derivatives. Chain rule, specifically here. So if you look at this first one, if I want to take the derivative of f of x, we have a function inside another function, the power being the outside function. When you take the derivative, you always do the outside function first, which would be the power rule. So the 4 comes out to the front, the new power is a 3. The inside, meanwhile, stays exactly the same. Then I have to take that and multiply that by the derivative of the inside. In that case, that would just be 8. To simplify that, I can multiply the 8 and the 4, which would give me 32. 8x minus 5 to the third. On the second one, I'm going to rewrite the function first. I'm going to write this as 7s cubed plus 3 to the negative 1/2. It's to the 1/2 power because of the square root, but then I move that to the numerator. Now it's negative 1/2 power. Now this looks a lot like this one did. Some function raised to a power, which is your most common power rule. So if I'm going to take the derivative of f of s, I'm going to pull the power out to the front. The new power would be 1 less than that, which is now negative 3/2. The inside stays the same. Then I have to multiply by the derivative of the inside. In that case, the derivative of this inside would be 21s squared. All right, simplify this a little bit. We're done. This is to a negative exponent, so I'll bring it to the denominator. This 2 is already in the denominator. I have this negative here. I have this negative, this 21s squared. So I get negative 21s squared over 2 times 7s cubed plus 3 to the positive 3/2. All right, so here we need to find the second derivative, and we're going to do this using the chain rule. I could use quotient rule, but it's actually easier if we rewrite this as 3 times 4t plus 5 to the negative 1. So if I go to take the derivative and I use the chain rule to do that, this negative 1 comes out, I get negative 3 times 4t plus 5 to the negative 2 times 4, which we could rewrite as negative 12 times 4t plus 5 to the negative 2. And I'm going to leave it like that, because remember, we have to take the derivative again. Normally, I wouldn't want that negative exponent, but it's easier to leave it that way to do the chain rule again. So now I pull that power out to get positive 24, 4t plus 5 to the negative 3 times the derivative of the inside is 4 again. And so I'm going to rewrite this for my final answer. 4 times 24 is going to give you what? 96 over 4t plus 5 all cubed. All right, so there's your second derivative. Okay, so now we got to do implicit differentiation. The key to implicit differentiation, there's a couple ways to do it, but the primary way that I showed you how to do it was to use partial derivatives. And one key to doing partial derivatives is that this has to be equal to 0. So I'm going to rewrite this as x to the 6 plus y to the 6 minus xy equals 0. Now this is that capital F of xy function we talked about. And so if I want to find the derivative of y with respect to x for this implicit equation, which is going to be the slope of the tangent line, slope of the graph, whatever you want to call it, if I do this, I need to take the partial of f with respect to x over the partial of f with respect to y and multiply that whole thing by a negative. So negative fx, I want to take the derivative of this with respect to x. When I do that, I treat y like it's a constant. So this with respect to x, since it only has x's in it, would be 6x to the 5th. This with respect to x, since y is a constant, this is some constant raised to the 6th power, which is all just one big constant, and the derivative of constant would be 0. So I'm going to have plus 0 minus the derivative of this with respect to x. Well, y is a constant multiple. It's multiplied by the x, and the constant multiple rule says we pull constant multiples out. It's like if I said, what's the derivative of 4x? The derivative of 4x would just be 4. You take the constant multiple, and you really just take the derivative of x, which would be 1, and you multiply them together. So same deal here. This would just be minus y. Then I do the same thing again, but with respect to y. So this with respect to y, x is a constant now. That's going to be 0. This would be 6 y to the 5th, and this one would be minus x, for all the same reasons. So your final answer would be negative 6x to the 5th minus y over 6y to the 5th minus x. Now you could take this negative and leave it on the outside of this whole thing. I could distribute this negative to the numerator. I could distribute it to the denominator, one or the other, not both. But it's fine to just leave it out here on the outside. So that's going to be your derivative of y with respect to x using implicit differentiation and using our method of partial derivatives. All right, for this one, we got to do a lot of the things we did in the last one, but a couple more. In this case, we're trying to find the equation of the tangent line to the given curve at the point. So remember, we have to use this y minus y1 equals m times x minus x1 point slope formula. We have the point already. This is the x, this is the y, x1, y1, and they'll go in their respective spots over here. Then we need the slope. Well, this is the slope of the tangent line, right? Because we're trying to find the equation of the tangent line. Well, slope of the tangent line is the derivative of y with respect to x. So this is an implicit equation. So basically, we want to find dy dx for this implicit equation, in which case we can do negative fx over fy. Well, we would want to write this in equal to 0 format, so it'll be x squared xy squared minus x squared y minus 48 equals 0. So there's your capital F function that we're talking about here. So again, negative derivative with respect to x. Y is treated like a constant. So this y right here is a constant multiple in terms of x. This y is a constant multiple in terms of x. So the first derivative with respect to x would be y squared, because the derivative of x is just going to be 1. Then this one, same deal, would be minus 2xy, and then the derivative of 48 is the derivative of constant, so that's 0. Then we go the other way and take the derivative with respect to y. Now x is a constant. So if this x is a constant, same deal, just the other way around, this would be 2xy minus x squared. Okay, so this is your derivative, which would give you the slope of the tangent line. Now, before when we did this, this used to only just have x's in it. Now we have x's and y. So when it comes to the point, we used to just take the x value for the point and plug it into the derivative. But now the derivative has both x's and y. It's dependent on x's and y. And that's mainly because this was an implicit equation versus explicit. So what we're going to do is to find the slope of the tangent line at 4, negative 2, so that we can plug it in here. We're going to plug 4 and negative 2 into here for x and y. So the slope of the tangent line at this 4, negative 2 point would be negative y squared, which would be 4 minus 2 times 4 times negative 2 all over 2xy, so 2 times 4 times negative 2 minus x squared, which would be 16. So do that computation. What do we get here? This is going to be negative 8, positive 16, and 4 is 20. So we get negative 20 over, here we're going to have negative 16, negative 16. So it's going to be negative 32. Simplify that, the double negatives give me a positive. The 20 over 32 would give me, what, 5 over 8? Okay. So 5/8 is my slope of my tangent line at 4, negative 2. So now I take that slope, I take this point, I use the point slope formula, and I got everything I need. So y minus negative 2 equals 5/8 times x minus 4. I'll multiply the 8 over so I don't have to deal with fractions. So 8 times y plus 2 equals 5 times x minus 4. So 8y plus 16 equals 5x minus 20. Bring all your x's and y's to one side, constants to the other, kind of cleans this thing up. So we end up with negative 5x minus 8y equals negative 36. There are a bunch of different variations of the same answer depending on which side. Sorry, this is plus y, plus 8y. There's lots of different variations of this answer, but this is one of them.